Good afternoon to all of you, whoever you have joined in this class. So, today's topic will discuss the separation method, the first unit, the general aspects of separation methods. In this unit, we'll give some introduction and its objective, then what are the different separation methods, scope of separation methods, classification of separation methods, and classification based on the property resulting in separation, then classification based on equilibrium and rate process, criteria for selection of separation methods. Okay, so in separation, so what do you mean by separation? If you see the definition, then it is the separation is a process by which a mixture is divided in at least two components with different compositions or two types of molecules with the same composition but different stereochemistry. That means we can separate two different substances into their individual components, and same substance if it will have different stereochemistry, like we have already known the stereoisomers, DL isomers, cis trans isomers, they can be separated. So that's why special reference is given that composition but with different stereochemistry. So different stereoisomers, if you can separate them, and if in a mixture, if the components they can be segregated, then that is the separation process. So the objective of this unit is, after studying you will appreciate the separation methods as a unified science, describe the scope and utility of separation method, discuss the evolution of chromatography, explain the classification of separation methods, and list the criteria of selection and separation methods. So, after knowing the definition, the objective of the, this subject is to analyze the different constituents of a mixture, procuring pure materials from complex mixture, and in analysis, we refer above in the first one, there may be three aspects: removal of interfering constituents before the actual quantitation of one or more known compounds, isolation of unknown constituents for subsequent characterization, analysis of a complex unknown mixture by subjecting the entire sample to separation into individual constituents. So, these are the introduction part. Then scope of separation method, or the use of separation method. Why we need to learn the separation science. So in our day-to-day life, you can see we are separating different substances, like isolation of various dyes for coloring purpose from natural material, and it also play a key role in our daily life. We remove undesirable gases and particles from the air we breathe. The municipal drinking water undergoes several purification steps. It is well known that the identification and removal of contaminants from food are largely possible due to separation process. One of the best example of use of separation in industry is the availability of a variety of products from crude petroleum. We generally separate different fractions of petroleum by fractional distillation. So a petroleum refinery or refinery industry, we are telling that one. Like then others, in a nutshell, there is hardly any walk of life where separation do not play their dominant role. In every stage of our life, we need some separation process. So chromatography will discuss later on. what are the different types of chromatography. Chromo means color, and depending upon the color or depending upon the rate of absorption and disruption, different constituents they are absorbed in the absorbing medium. So we'll get different types of chromatography. If your absorbing medium is a plate or simple paper, then we are telling it is paper chromatography, like column chromatography. Okay, different types of chromatographies are there, so we'll discuss this one later on. Then the classification of separation methods in a broad view, you can say. The separation methods, it depends upon some physical and chemical properties. Depending upon there, we have different types of separation methods. The main properties which results into segregation of components of the mixture are volatility, solubility, partition, ion exchange, surface activity, molecular geometry, and electromigration. So the volatility, that means it depends upon the volatilization or volatility of the substance. The method based on volatility mainly include vaporization and distillation, and also sublimation. Sublimation is a special case of distillation where a solid is directly vaporized without passing through a liquid state. So vaporization is simple, where solvent is removed by using heat or air current such that the material concentrate into a solid. So different types, the various types of distillations are fractional distillation, flash distillation, vacuum distillation, steam distillation, and azeotropic distillation. So we'll define all these terms in a nutshell. So what is fractional distillation? It involves the return of condensate to the distillation unit under conditions such that this condensate is continuously and countercurrently in contact with the vapors. By this method, you can achieve greater enrichment of vapors of more volatile components than that obtained by simple distillation. Best example of fractional distillation is refining of petroleum. Distillation of petroleum to different fractions. So depending, I can imagine, or if you have the idea, you can just recall. In a fractional distillation, you have the distillation column with different stages. The components of petroleum, it moves, so it will condensed. So which fraction will have lower boiling point, that will condense at the top, and which will have higher boiling point, that will condense at the bottom. So like that, we have to separate different fractions of petroleum, like petroleum ether, petrol, diesel, kerosene, mobile, all these things, and finally we'll get the coal tar. All these things are the examples of fractional distillation. Then in flash distillation, there is an instantaneous and continuous vaporization of a definite component of the mixture such that the total vapor produced in equilibrium with the remaining liquid. Am I audible? Hello? Hello? Okay, I think I'm audible. So then the vacuum distillation. Please mute your mic. Okay, anyway. Vacuum distillation is actually distillation under reduced pressure. It is used to separate high boiling mixtures or liquids that decompose below their normal boiling point. Low pressure reduces the boiling point. As you know, if you decrease the pressure, boiling point will decrease. So if any compound which is which decomposes at its boiling point or just near to its boiling point, it will decompose. In such case, how to distillate or how to separate that fraction? Then we use the vacuum distillation, so that when you reduce the pressure, boiling point will decrease, and so that the compound will not decompose. Then steam distillation. Generally, it is employed to separate the components from a non-volatile impurity. The boiling temperature of the mixture is reduced by vaporizing it in a stream of carrier vapor, say steam, which upon condensation is immiscible with original mixture, and thus a separation can be readily achieved. I think I am clear. In steam distillation, what you think in steam distillation generally used for separation of essential oils. Essential oils, they are soluble in steam. That means they can vaporize along with steam, and it will come out of the distillation container. So when it will cool down, then steam will be condensed to water, and that essential oil, it will form the oil. So you will get a water and oil, two different layers. Then you can separate. But at higher temperature, the compound, the essential oil, is soluble in steam. That's why along with steam, that essential oil will come out. Then azeotropic distillation is used for separating components of a mixture which boil very close to each other. The relative volatility of the components of the mixture is altered by adding another substance. This description will give you an idea about the different way of distillation that can be carried out in different types of mixture. So, azeotrope, as you know, azeotrope means azeotropic mixture is such a mixture which cannot be separated, and in azeotropic mixture, according to Raoult's law for non-ideal, this is non-ideal solution. So in that case, two substances which will form the azeotropic mixture, each of the substance will lower the boiling point of the other. That means the azeotropic mixture will have a common boiling point, and the boiling point is less than both the components. So that's why it is used separating the components of mixture which boil very close to each other, so that one will form azeotropic mixture. That means it will not come out of the mixture. The other will not form the azeotropic mixture. That means will it can be separated. See, if the two components are there in the mixture, you have to add a third component which will form azeotrope with either of the one. So that if the two components A and B, for example, they have narrow boiling range, so when you are let B is forming azeotrope with the component C what we have added, so now B cannot be separated from C, but A can be separated from B. So that's the point. So we can use the azeotropic distillation in such case. Then depending upon the solubility. So solubility means separation. In separation is essentially implies precipitating the constituent of interest from the solution. So it is soluble. So we have to precipitate the solute from the solution. So that means it depends upon the solubility. You increase, for example, if a solute when forms solution, so if the reaction is endothermic, so with increase in temperature, more and more solute will go into solution. So when you decrease the temperature, ultimately it will form one supersaturated solution. So by decreasing the temperature, whatever extra amount of solute has gone into solution, that will come out, and that will be pure in its purest form. The impurity will remain in the solution. So depending upon the solubility at a particular temperature, we can separate the components. This process is carried out in an appropriately selected solvent and in a controlled manner. It can lead to crystallization. So precipitation can be brought about in a number of ways, out of which some important ones are discussed here. Important are partition, like liquid partition chromatography. We'll use that one, gas liquid chromatography, ion exchange. All depends upon the solubility. So solvent precipitation, okay. Then after solubility you have the partition. Partition means depending upon the adsorption or the mixing of one component with different solvents. This method based on partition which require two phases, and there has to be a redistribution of components between these two phases. Some important types of methods are liquid-liquid extraction, liquid-liquid partition chromatography, gas-liquid chromatography. All these are there. So in liquid-liquid extraction, already you know this one partition coefficient of iodine between benzene and water. Iodine is more soluble in benzene, less soluble in water. So in that case, we can separate impurity. Impurity is more soluble in water, less soluble in benzene. So depending upon, we can separate. So some other things are also written here. It is known as solvent extraction. When solute is brought in contact with two immiscible solvents, one of which is invariably water and the other is organic, then it distributes itself in them in a fixed ratio. In certain favorable conditions, this solute of interest can be more or less completely transferred from one phase to another. This purification technique finds application in separation, purification, and enrichment. We'll discuss this one later on. Then, in liquid-liquid partition chromatography, there is a support which holds the stationary liquid phase, and a mobile liquid phase runs over it. Because of the requirement that the two liquids be immiscible, it follows that they differ markedly in polarity. So, in liquid partition chromatography, you are also reverse phase chromatography. Liquid extraction is discussed as we discussed above. Then column liquid partition chromatography. All these things we will discuss in detail. You have also SPLC, high pressure liquid chromatography. Okay. Then high pressure thin layer chromatography is also available. Everything we will discuss. Then gas liquid chromatography, the stationary phase is a liquid coated in a column or in a support packed in the column. So then ion exchange. In solubility, you have ion exchange. In ion exchange, there is an exchange of ions, cations or anions between an insoluble solid material and the solution in contact with it. The solid material is called ion exchanger, which carries exchangeable cations and anions. When the exchanger is in contact with an electrolyte, these ions can be exchanged for a stoichiometrically equivalent amount of other ions of same charge. Carriers of exchangeable cations are known as cation exchangers, and carriers of exchangeable anions are known as anion exchangers. Certain materials are capable of both cation and anion exchange and known as amphoteric exchanger. So generally, an exchange is performed in columns. However, in some cases, batch operators are also carried out. In the surface activity, it is the property of adsorption which is mainly used for separation. Liquid solid adsorption chromatography, gas solid adsorption chromatography. Everything what we will discuss here depends upon the adsorption or selectivity and mainly the chromatography. In liquid solid adsorption chromatography, an active adsorbent acts as a stationary phase and the liquid as the mobile phase. The stationary phase can be in the form of a column or a thin layer or on a glass plate. Paper chromatography cannot be exclusively classified as liquid partition chromatography. If the cellulose of the paper is playing an active role as an adsorbent, it will be justified to put it under the head of adsorption chromatography, not on liquid solid. In gas solid adsorption chromatography, the carrier gas with the volatile component of the mixture flows over an active adsorbent packed inside the column. Because of the difference in adsorption affinity of the components, the segregation of the components takes place. As compared to gas liquid chromatography, in which a liquid is coated over inert material packed inside the column, here gas solid chromatography and adsorbent is packed. Detail we'll discuss later on. Then, basing upon the molecular geometry, you have molecular sieves and gel filtration. That is, okay. So, gel formation or size exclusion chromatography is the technique which is based upon the molecular geometry. There is a number of methods based on molecular geometry. They require a permeable barrier to provide separation. The methods are based on the molecular sieves and gel filtration. The permeable barrier separation process of practical importance utilizes semi-permeable membrane as the restrictive surface. So, different types of membrane available, which are maybe microporous membrane, homogeneous membrane, charged membrane, and thin membrane. Similarly, there are numerous applications of this membrane. Some are ultrafiltration, reverse osmosis, dialysis, electrolysis, all these things. And in case of gel filtration, you have the gel permeation or size exclusion chromatography (EPC). Then we'll move to electromigration. The simplest example of separation by migration under electric field is controlled potential electrodeposition. This method is quite effective for the separation of certain metal ions in the presence of other metal ions. But in the normal classification of separation method, it is not given due to recognition. However, the techniques like electrophoresis, electrochromatography, in which an electric field is utilized to produce or affect the relative motion of the charged species in the solution, they are classified on this category, that is electromigration. The two frontline techniques include under this header electrophoresis and electrochromatography. No electrophoresis, only the electric field causes the motion, while in electrochromatography, the movement is caused by resultant of an electric and a gravitational force. Electrophoretic separation are performed in two different ways. One is called slab electrophoresis and the other is capillary electrophoresis. In slab electrophoresis, we use a filter paper or porous glass or a gel cast in the form of a bed, and samples are introduced as spot or band, and a DC potential is applied across the slab for a fixed period. Then separation takes place. Like TLC, you can visualize, then you have to separate the spot. In capillary electrophoresis, a buffer filled capillary tube is used. The tube extends between two buffer reservoirs that also holds the platinum electrode. So the sample is introduced in one end and a DC potential is applied. Separated analytes are observed by detector at the other end. Simplest form of electrochromatography used is by fusion of electrophoresis and paper chromatography. The sheet of paper is usually suspended vertically with the solvent or the paper descending from the top. The electric field is applied horizontally along the side of the paper. The capillary electrochromatography is a more sophisticated version of paper chromatography. Then classification based on equilibrium and rate process. So depending upon the rate of reaction, it may be physical or chemical, that is adsorption, rate of adsorption, all these things. So which we have already discussed, they are divided into various classes like equilibrium and rate process as criteria. The equilibrium process are based on differences in the properties of individual components. These processes are generally based on phase equilibria and involve the distribution of substances between two phases. Rate processes are based on the kinetic properties of the components. So this classification, now different types of classification based on equilibrium process. It has been pointed out in the preceding section that equilibrium processes, there are two competing phases and they could be as follows: gas liquid or gas solid, liquid liquid or liquid solid. In gas liquid, some of the important methods in which gas and liquid are the two phases involved as follows. Non-chromatography, we have distillation and foam fractionation. Distillation already we know, which involves gas and liquid which are in equilibrium. Foam fractionation, we know the fourth flotation method by which the sulfide ores can be concentrated. So that is foam fractionation. When we say distillation, it means distillation in all its forms. The well-known example of foam fractionation is concentration of ores by froth flotation process. It's given here. Then in chromatographic method, we have gas liquid chromatography. Okay, this is all about the gas liquid equilibrium process. Then the second one is gas solid. That means when two phases are gas and solid. Few examples are non-chromatography. In non-chromatography method, we have sublimation and adsorption, where gas and solid they are in equilibrium. Okay, adsorption means one gaseous adsorbent, maybe it is adsorbed on the solid absorbing medium. So it is a gas solid equilibrium, and sublimation you know. And in chromatography method, we have gas solid chromatography and exclusion chromatography or size exclusion chromatography. In case of sublimation, the solid is directly vaporized and the equilibrium exists between the gas and the solid. Adsorption of gases by solids is a well-known method for separation of these forms, is basis of gas-solid chromatography. Exclusion of molecules based on shape and size of both gas and liquid can take place in exclusion chromatography. And in liquid-liquid equilibrium system, both the phases are liquid. Two immiscible liquids come in contact with each other. Okay, not miscible. Here the separation takes place because of favorable partition of one or more components in one of the phases. In non-chromatographic method, we have liquid-liquid extraction. In chromatographic method, we have liquid-liquid column chromatography, liquid-liquid vapor or planar chromatography, high pressure liquid chromatography. These are in liquid-liquid equilibrium method. Then liquid-solid. In non-chromatographic method, you have precipitation and fractional crystallization. And in chromatography method, we have adsorption chromatography, that is column or planar or paper chromatography, ion exchange chromatography, affinity chromatography, gel permeation or size exclusion chromatography. Then the classification based on rate processes. The separation based on rate processes take place due to difference in the kinetic properties of the components of the mixture. The separations are mainly achieved due to the following two reasons: different diffusion rate through permeable barriers such as membrane, then different migration velocities under various fields like electrical, gravitational and thermal. So when you are using electrical field or gravitational field or any thermal gradient will be there, then migration velocity of some component, one component will differ from that of other. So basing upon that, they can be separated. Similarly, if diffusion rate of diffusion will be different for different components. Two gases, for example, one is having high molecular weight, one is low molecular weight. So the low molecular weight gas will diffuse faster than high molecular weight. According to Gram's law of diffusion, as you know, the molecular rate of diffusion is inversely proportional to the square root of vapor density, or the square root of molecular weight, you can say. So if molecular weight will be more, rate of diffusion will be less. So low molecular weight compound, rate of diffusion will be more. So depending upon the rate of diffusion also they can be separated. So that is based upon the rate process. Similarly, different diffusion rate through permeable barriers. Some example is given here. The most commonly used permeable barriers are semi-permeable membrane, which are used in ultrafiltration, reverse osmosis, dialysis, electrodialysis, all based upon the rate of diffusion. Like then field separation, second one, different migration velocity under various fields. In field separation, electrical field is commonly used to affect separation, and the different methods which are based on application of this type of field are electrodeposition, electrophoresis, capillary electrophoresis, and electrochromatography. So the examples for separation resulting due to application of gravitational thermal fields are ultracentrifugation and thermal diffusion. All these things you have, I think you know. Then the criteria for selection of separation methods. So how will you choose the separation method? Particular separation method to separate the different components. Selectivity, detectability, yield, speed and convenience, capability for hyphenation, and ease in scaling up and economics. We'll discuss a little bit about these processes or these criteria. Different. What are the criteria? The first one is selectivity. The foremost and most important is the selectivity. The selectivity relates to the capability of the technique to separate the desired component effectively from a complex mixture, particularly containing closely similar components. The term effective separation is expressed in terms of resolution, separation factor, decontamination factor, and percentage purity. All these terms in one form or the other will appear in different units of this form. Okay. Resolution, separation factor, decontamination factor, or percentage purity, or the retention factor, all these things are there. How to separate? So the selectivity, that means which technique will select for a particular separation of a particular mixture. So selectivity is the main criteria. That detectability. The term detectability refers to the minimum amount that can be detected. It is also termed as sensitivity. In the case of detector, it can be calculated based on certain assumptions such as detection at 2 or 3 times the noise level observed at the baseline. You understand this thing? Detection at 2 or 3 times of the noise level observed at the baseline. So when we are, for example, any chromatography or any separation technique like HPLC, whatever it may be, we have some baseline correction and noise level. Noise level is how to detect. When you are detecting basing upon the IR spectra, or you can say UV visible spectrophotometer, in that case you can detect all these things. So the instrument, it will have some equation. So if contamination is there, then noise will be produced. So noise means if the plot should be a straight line, but due to noise it will be like zigzag manner, the plot will curve. So then how to detect the peak? So that's why it is written here, the detection at 2 or 3 times the noise level. If noise level peak will be like this much, then the peak of the sample should be more than 2-3 times, twice or thrice of the noise level. Then only we can detect. So that is, so where this thing will happen, that detector we have to use. So detectability. So it is also another criteria. Sensitivity can also be determined practically. Sensitivity can be improved by properly optimizing the separation condition using the same detector. Sensitivity assumes paramount importance when the quantity of mixture to be analyzed is very small or trace impurities for obtaining an ultra pure material. So detectability or sensitivity is the another important issue. Reproducibility. The method should be such that it gives reproducible result of separation. It is usually expressed in terms of standard deviation or coefficient of variation based on replicate measurements. So we have to take 2-3 measurements. If you are getting the same result, then we can say our detection method is accurate. Otherwise, we have to choose some other technique. Okay, so reproducibility is the major criteria or another criteria. Now at this point, it may be important to point out that separation conditions should not be such that a slight variation in the conditions may alter the result significantly. Reverse must be there. If there will be significant variation, the result does not alter, then that will tell reproducibility. But this thing, whatever it is, if slight variation of the condition will be there, then the result will alter significantly. This should not happen. A flexibility in the condition of separation is always preferred. This is particularly important if the process is to be scaled up on a commercial scale. Then yield, speed, and convenience. In all those methods in which a simultaneous quantification of the separated product is done, a quantitative recovery of the separated product is a must. Naturally, a method giving a higher yield is preferred. In case where the yield is not high, the remaining portion may have to be recycled. Okay, speed of separation is another criteria, because if you take months for separation, then we cannot spend much more time there. So any technique which is awfully slow in achieving the separation goes in the background. By properly adjusting the experimental parameter, it is sometimes possible to improve the speed of separation process. Speed as a criteria assumes great significance if the constituents radionuclides with very short half-life. So that's why when radionuclide, radioactive substance we have to separate, then speed is the most important criteria, because they have, if it will have a very short half-life, then there will be decomposition. So in such situation, speed becomes more important than the yield. Then the hyphenation, capability for hyphenation. That means hyphenation means you can use two methods for separation like this GCMS. Whatever. In a majority of chromatography method, there is a detector which quantifies the effluent coming out of the column. These detectors are not very sensitive. Also, they have a limited capability of identifying the unknowns. It is known that mass spectrometer is a very powerful universal detector. Therefore, it's being interfaced with some of the chromatographic techniques. A very important example in this regard is interfacing of a gas chromatograph with a mass spectrometer, so GCMS. Gas chromatography is an ideal separator, whereas mass spectroscopy is excellent for identification. The aim of an interfacing arrangement is to operate both a gas chromatograph and a mass spectrometer without affecting the performance of either instrument. The problem is compatibility. The interface provides the link between the two instruments. A similar line, gas chromatography, is coupled with also with infrared spectroscopy. Okay, the techniques like high performance liquid chromatography and simple liquid chromatography are coupled with mass spectrophotometer, just like GCMS, HPLCMS, mass spectrophotometer. The interfacing makes the technique as a powerful analytical tool. Thus, in nutshell, a separation technique is conveniently interfaced with another effective detecting device like mass spectrometer or spectrophotometer. This can be additional advantage of the technique. There have been serious efforts in this direction, and even the simple techniques like thin layer chromatography has been interfaced with mass spectrometry. There is in scaling of and economics. It has been repeatedly pointed out that one of the main roles of the separation in technology is in the synthesis, recovery, and purification of products. Therefore, the separation method do not remain necessarily confined to the bench scale. The basic data has to be used to scale up the process to pilot plant scale. The method should be such that it can be conveniently scaled up on a commercial scale without much alteration in the commercial scale, without much alteration in the basic experimental parameters. Once we talk of the use of the method on a commercial scale, the economics of the process figures in. Not only the economics, the environmental consideration also having significant importance. Okay, so the commercial methods of separation should be environmental friendly. So in a nutshell, what we have discussed in this unit, it provides an introduction to the course on separation method. It highlights the utility of separations in the analysis and recovery of pure products from complex mixtures. The scope of separation extends from the needs of everyday life to complex technological processes. There is hardly any branch of science or technology which has not been a beneficiary of the development in separation science. So, separations encompass different physicochemical principles, and the subject has itself matured to a unified science. So, different phenomena we have already discussed. So, this is all about the introduction. There are some terminal questions there that you so we can do or analyze. Some answers are also there, self-assessment questions. Want any further reading, then you can go up the books, some reference also there. Okay, we'll have just 5 minutes break, then we'll start the second unit at the solvent extraction. Okay, so we'll start the next chapter, the solvent extraction.
Sir, you are not audible.
I'm not audible. Hello.
No, sir. Now it is audible,
Okay.
but screen is also not visible.
No, no, I will share. Just 1 minute.
Okay, sir.
Is it okay now?
Yes, sir. Yes, sir. It is okay now.
Okay. Thank you. So the second unit, that is solvent extraction, as the objectives are here. So general principles and terminology, phase rule, consideration, distribution law and its limitation, distribution ratio, percentage extraction, all these general principles and terminology. Then classification of extraction systems, distribution of simple molecules, then extraction by compound formation, solvation, ion pair formation, brown ethers, diluents and modifiers. These things will be discussed in this unit. So directly we move to the phase rule. Already you know about the phase rule put forward by Gibbs, or as remember or recall. So what is that phase rule? P plus V equal to C plus 2. So what is P? What is V? Here V is written, or you can say this is degrees of freedom. F, P plus F equal to C plus 2. As we already studied is general consideration. P plus F equal to C plus 2. P is the number of phases, where P is the number of phases. V is the variance or degrees of freedom. So that's why I told F. P plus F equal to C plus 2. C is the number of components. So how will you define a phase? You can write the definition if it is not here. So phase is that part of the system which is uniform throughout and can be separated from other similar part of the system by a boundary or by a surface of separation, and there exists a dynamic equilibrium between the two phases, between the other parts, like this you can say. That means phase, I repeat again the definition, phase is that part of the system which is uniform throughout. Why I did not tell homogeneous? Homogeneous means, again you have to define what is homogeneity. Homogeneity means if the concentration remains same. That's why I told uniform throughout, or you can say homogeneous. So for phase is that part of the system which is homogeneous and can be separated from other similar parts of the system. That means another part of the system, if it is homogeneous, this part of the system is homogeneous, then that means you can say these are two different phases and there exists a boundary. That means in a nutshell, phase is physically distinguishable and mechanically separable. Okay, phase is that which is physically distinguishable and mechanically separable. This much if you define, then it's okay, but you have to fine tune the definition. It should be homogeneous. Phase should be homogeneous throughout, and if the system consisting of two phases, then if there exists a dynamic equilibrium between the two phases, then we can apply this rule, that is phase rule. P plus F or P plus V equal to C plus 2. Okay, one simple definition or example I am giving. Let us consider water and oil, or water and kerosene. I'll specify the oil as kerosene. So water and kerosene, they constitute two phases because they are physically distinguishable. If you mix water and kerosene, you stir it and keep it for some time, then two layers will be separated, kerosene at the top and water at the bottom. So physically they are distinguishable and you can separate mechanically. That means by using a uh, separating funnel, you can separate kerosene and water. And if you want to apply phase rule, then what is the extra criteria or extra definition you have to add there? There must exist a dynamic equilibrium. Otherwise, you cannot apply phase rule. Means after must some particles of water they move from water to kerosene. Simultaneously, some part of kerosene
Sir, there is a noise, sir.
from where? What type of noise?
Sir, you are not audible, only noise is audible.
How is it possible? Due to mic or something? Hello? Now is it okay? Hello? No. Hello?
Voice is very low.
Hello? Hello? Is it okay now? Am I audible?
Sir, I think there is a loose connection of your headphone.
Hello? 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 Am I audible now?
Yes, sir, but there is an extra noise with your voice.
Still noise I see. No, noise are there. Hello?
Yes, sir.
Am I audible?
Yes, sir, you are audible.
Okay. Okay. So we are discussing phase rule. So yes. So if you take a system containing oil and water, it consists of two what? Transition of particles to water layer or water particles to oil. So that's why we cannot apply phase rule there. Consists of two phases, but phase rule cannot be applied. So this dynamic term must be there. For example, if you take saturated solution of sodium chloride, so that means the system consisting of sodium chloride solution and some sodium chloride solid. So between sodium chloride solid and sodium chloride solution, you have the dynamic equilibrium. That means some sodium chloride solid, they are coming into solution simultaneously. From solution, sodium molecule to the solid state. So that means it consists of two phases, one liquid containing sodium chloride solution, another is solid containing solid sodium chloride, and there exists an equilibrium between the two phases. That means we can apply the phase. So that is the idea or definition of phase according to phase rule. Then what is the component? That means the different entities, the chemicals they are present in the system, and the minimum number of such species by which the total system can be explained is known as number of the minimum number of species by which the whole system can be explained or expressed is known as. For example, you have a system containing ice, water, and water vapor. So number of components is one. Ice also formula is H2O. That is H2O, water vapor is also H2O. So we have three components. Another example I'll give. For example, you are heating calcium carbonate in a closed container. Can you imagine? You heat calcium carbonate, it will be converted to calcium oxide and carbon dioxide. So in a closed container, that means now the equilibrium will be established between the reactant, that is calcium carbonate, and the product, that is calcium oxide and calcium carbon dioxide. Can you tell me the number of components in the system? Now the different chemical species are there which are present: carbonate, calcium oxide, and calcium dioxide. Three species of three chemical species are there. What is the number of components? Two, three, or one? Anybody? Hello? Am I audible? Am I audible?
Yes, sir, you are audible, but there is a sudden
Okay,
rise
can you
and
tell
fall
me
in
the
your
number?
voice.
Hello? Hello. Okay. In this case, the number of components are two. Any two out of these three, if you take, the total system can be explained. So number of components are two. Then degrees of freedom means by how many dynamic variables are responsible to express the system. Okay, so that is the degrees of freedom. It may be temperature, pressure, it may be pressure and number of components, or temperature and number of components. So when we are dealing with two phases, two immiscible solvents and one solute distributed between them, therefore variance will be unity. Degrees of freedom will be unit. Two immiscible solvents, one solute distributed them. So that means now number of components 3. This will amount to the fact that concentration of the solute is one phase, will fix the concentration of the solute in another phase. There will be definite relationship between the solute concentration of the two solvent phases, so that this ultimately on the basis of distribution. So distribution law, that is the Nernst distribution law, for our value Nernst. Okay, so according to this law, it can be stated as a solute will distribute itself between two immiscible solvents in such a manner that at equilibrium, the ratio of concentration of the solute in the two phases at a particular temperature will be a constant, provided the solute has the same molecular weight in each of the phases. That means the solute will not undergo association or dissociation. So if the molecular weight of the solute remains same in the two phases, then it will distribute itself in such a manner that the ratio of the concentration of the solute in the two phases at a particular temperature will remain constant. Let S is the solute which is distributing between solvent 1 and 2, then we can write S1 is in equilibrium with S2. That means concentration of solute in solvent 1 is in equilibrium with concentration of solute in solvent. KD, that is the distribution coefficient or extraction coefficient, that is equal to, according to this Nernst distribution law, it will be S2 concentration of solute in solvent 2 divided by concentration of solute in solvent 1. So it is independent of the total concentration of solute and is volume. So hence concentration of solute in solvent 1 and concentration of solute in solvent 2 denotation is like this. So if you imagine that total concentration to be increased until one phase is saturated and reaches the concentration saturated solute in solvent 1, the second phase must be simultaneously become saturated solution of concentration of solvent, sorry, solute S in concentration of solute in solvent 2, that is saturated. So the distribution ratio again S becomes the ratio of the solubility of the solute in the two phases. This expression holds well for materials which are extremely sparingly soluble. This law is a useful approximation for the distribution of species in two phases. Careful experiments reveal two serious shortcomings. The first one is when the distributing species is involved in a chemical reaction such as dissociation or association and is changed in either case. So there's, as I told, there should not be any association or dissociation. The molecular weight of the solute must remain same in the two phases. Typical case is real distribution of benzoic acid between water and benzene. In the aqueous phase, benzoic acid is partially ionized, while in benzene it is partially dimerized by hydrogen bonding in carboxyl. So what happens in case of water? It is hydrolyzed, molecular weight decreases. In benzene, in organic solvent, it dimerizes, the molecular weight increases. So the ordinate equilibria dealing with within this case will be discussed in the next sources. Okay, in the extraction of metal ions, the existence of single species can be properly accounted for while considering the distribution of species in two phases. Then the second shortcoming, because of Nernst's law stated, is thermodynamically rigorous. Strictly, in the thermodynamic term, it is the activity ratio rather than concentration ratio that should be constant. In other words, the thermodynamically rigorous partition law would be stated as the activity of a chemical species in one phase maintains a constant ratio to the activity of the other phase. This precisely defined ratio known as thermodynamic partition coefficient or distribution coefficient radius. We are giving the activity. The solubility, that means concentration of solute into activity coefficient. So here we are given the activity. So S is curly bracket S represents the activity of the solute, and gamma mu is the activity coefficient. So to multiply concentration into activity coefficient, you will get the activity. Okay. Then we move to the distribution ratio. We already observed that a single species may be present in two phases, but as an analytical chemist, for the purpose of separation, you are concerned while overall or stoichiometric distribution of the components of interest in the two phases. Therefore, to describe the extraction, there is a more practical quantity known as the distribution ratio. So the distribution ratio, or D, it is the total concentration of solute in the organic phase divided by total concentration of the solute in aqueous phase. In an ideal condition, if there is no interaction in either phases, D would be the same as Kd. If all the interactions of distributing species are known, they can be evaluated as an expression showing the effect of various parameters on D. So distribution of benzoic acid between benzene and water, that already we have discussed little bit idea we have given, that it will dissociate in water and it will associate in benzene. So what is the equilibrium condition that we have to see here. So in aqueous phase, as you know, benzoic acid we have written here HBZ. In water it will produce H3O plus and Bz minus, benzoate ion and hydronium ion. Similarly, in benzene phase, there will be partial dimerization. That means two benzoic acid molecules, they will combine to form the dimer. So equilibrium will be established like this. So therefore, the three species, that means benzoic acid, benzoate ion, and dimer of benzoic acid will have their own Kd value. To see here that first one, the benzoic acid. So that will be benzoic acid in water, or sorry, organic solvent divided by benzoic acid in aqueous. That is the actual term of distribution constant Kd. But what will happen in case of the benzoate ion? You can say benzoate ion in organic medium, organic solvent, and benzoate ion in aqueous. Similarly, dimer, it will also have partition coefficient. So dimer in organic and dimer in aqueous. So total D will be now total benzoic in aqueous phase, sorry, in organic phase, this one, divided by total benzoic in aqueous phase. So in benzoic, here you have benzoic acid and the dimer in organic, and in aqueous you have the benzoic acid and benzoate ion. So it is evident that D will not remain constant over a range of experimental conditions, because if you increase the pH, then what will happen of the aqueous phase? The D will be lower. Why? Because this benzoic acid, this concentration, if you increase the pH, that means you make the solution alkaline, so more and more benzoate ion will be formed. So the result T will be decreased. This is with the benzoic acid will become benzoate ion. Does not extract in the phase. Similarly, another example, distribution of osmium tetroxide between carbon tetrachloride and water. Osmium tetroxide, when it reacts with water in aqueous phase, it exists as a dibasic acid, that is H2OSO5, react with water producing H2OSO5. So it will remain as a dibasic acid which partially dissociated to H plus and HOSO5 minus, and second phase will give H plus and OSO5 2 minus. And in organic phase, osmium tetroxide forms a tetramer. Four molecules of osmium tetroxide tetramerize to produce the tetramer. So now what will happen in this case? You can see here same thing as in case of benzoic acid. If you analyze the total scenario with regards to the presence of osmium in its different forms of the two phases, simple. Osmium tetroxide monomer will be only situated in both the phases where this dibasic acid H2OSO5 and the charged species, the monocation, monoanion and dianion, it will remain totally in aqueous phase, while the tetramer it will remain in the organic phase. But the total concentration of osmium in organic phase divided by total concentration of osmium in aqueous phase will be the monomer in organic phase plus the tetramer. Okay, then the monomer, the compound in aqueous phase, its acid, its counter ion, monobasic and dibasic anions will be there. So this will be the total representation of the value. So the value of D, or the total osmium concentration in the two phase, can be calculated if the value of equilibrium constant of the reaction no. So in the two equilibria, one of benzoic acid and the other osmium tetroxide, the distribution ratios have been presented in terms of concentration of certain species. So now the percentage extraction from the distribution ratio is merely a concentration ratio, and the extent of extraction will therefore depends upon the volume ratio of organic to water phase. Since we are mainly interested in the context of the extent of extraction, we go for another practical term, which is the percentage extraction or percent E. Let F be the fraction of the total metal in the organic solvent at equilibrium. Okay, then 1 minus F is its fraction in the aqueous phase. Let VO and VA, that means the volume of organic and volume of aqueous phase respectively, then D will be equal to total metal in organic phase divided by total metal in aqueous phase, concentration of metal in O divided by that of phase. So concentration of metal in organic phase, that is fraction of the total metal divided by volume, so F by VO, whereas concentration of metal in aqueous phase is 1 minus F by VA. Okay, so now if you just cross multiply, so it will be F into VA divided by 1 minus F into VO. So it will be like this. So D into VO, so just cross multiplication. So F, the fraction, it will be D into VO, that means organic, volume of organic divided by volume of aqueous into D into VO. So percentage of metal extracted, so that will be 100 into F, just multiply. So this will be 100. So if the volume of two phases are equal, then the denominator simplifies to D plus 1, this one. equal, so it will be 1. So 100 is B divided. Means the volume of both organic and aqueous phase you have taken in equal amount. Then, so it can be, so we'll plot a graph taking the percentage extraction and distribution ratio. So graph will be like that. So the percentage extraction, the useful term. So this figure shows the concentration of interconversion of D and percentage extraction in a unit volume ratio. It can be seen from the plot that when the extraction efficiency approaches 100%, the distribution ratio approaches infinity as a limit. For the extraction to be in the range of 99 to 100%, the distribution ratio will vary from 99 to infinity. Such a large difference in the distribution ratio is 99 and infinity may be misleading when in reality the extraction will be nearly complete in both the cases. Then look the separation factor. Solvent extraction, it is basically a separation technique. The main objective is to separate the desired constituent from the other substances present in the mixture. So in order to achieve the objective, you look for a solvent extraction system which may quantitatively extract the required constituent with practically negligible amount of impurities present. So that's why we'll express this. The effectiveness of separation is usually expressed by means of separation factor, that is beta, which is related to the individual distribution ratio in the following manner, that is concentration of component 1 in organic to concentration of component 2 in organic divided by concentration of component in aqueous to that. So okay, so which is equal to d1 by d2. So d1 and d2 are the distribution ratio component 1 and 2. For a good separation, beta should deviate from unit and largely as possible. The ingenuity and knowledge of a separation chemist is tested to find whether the conditions where beta should be deviate from unit. So with the available data, as you can see, so we'll achieve this one. Then the multiple extraction. It is simple where one short contact between the two phases is made. The two phases are second until the equilibrium is attained. So multiple extraction. That means what we have to do here, two phases which may brought together repeatedly, the following four types of situation may be visualized. So when you are checking first one, the two phases, then they will be in contact with each other. So you have to check this till the equilibrium is attained. Then one phase could be brought repeatedly in contact with the phase portion of the second phase. This situation would be applicable where one substance, it will remain quantitatively in one phase while the other one was distributed in the two phases. This would be like the repeated extraction of an aqueous solution with successive portions of an organic solvent. In the third case, in this case, one phase move while in contact with the second phase, and second phase it will remain stationary. So It is actually known that this discontinuous concurrent or pseudo countercurrent it is used. The fourth case, it is really the countercurrent in which both phases move continuously in contact with each other but in opposite direction. True example of countercurrent is the fractional distillation. This multiple extraction with successive portions. So in this case, let V milliliter of solute in phase 1 derive the expression. In this procedure, a given volume of solution is brought in contact with a solvent until equilibrium is attained. Even if we suppose that none of the interfering substance is extracted, the completeness of extraction is a very important factor. Okay, so let V1 milliliter of the solution that in phase 1 containing W gram of solute is contacted to equilibrium with V2 milliliter of another solvent that is phase 2 immiscible with the first. Let W1 is the weight of the solute remaining in the phase 1 after equilibrium is attained. Now the concentration in phase 1 that means C1 is how much? W1 by V1 gram per milliliter. Similarly, the concentration in phase 2 we have taken W and W1 is the weight solute remaining in phase 1. So in phase 2 it will be W minus W1 divided by V2 gram per milliliter. So therefore D will be how much? In phase 2 divided by C2 by C1 only. So it is W minus W1 by V2 divided by W1 by V1. So by plus multiple W1 will be W into V1 divided by dV2 plus C1. So if we again extract phase 1 with another portion of V2 milliliter of the solvent, then what will happen? W2 gram will be the weight of the solute remaining in phase 1. So like this will go for successive extraction. So now same formula we put, then W2 that will be equal to W1. Here W will become W1, then V1 dV2 plus V1. So because from when you are adding another portion of the solvent, if W2 will come into the second phase and W2 will remain in the first phase. So W2 will be like in place of W1 will put W2, in place of W will put W1. Rest will remain same. Like the successive W2 will get this one it will be square again. If you put there on like that, if W1 n type of successive extraction if you do, then Wn will be W into this to the power n. So the fraction remaining in phase after n extraction will be Wn by W. So it will be this one. So, and the fraction transferred to phase 2 will be F2 which is equal to 1 minus F1. If phase 1 is aqueous and phase 2 is organic, then percentage extracted will be equal to 100. So for the most effective extraction, V2 should be taken as small as possible and N as great as possible for a given amount of solvent. This amounts to the fact that the best results are obtained by relatively large number of extraction with small amounts of solvent. Okay, then we'll move to classification of extraction systems. So, three steps already we have discussed: formation of an uncharged complex or extractable species, distribution of extractable complex or the species, interaction of complex or the species with organic phase, this association or dissociation. These things already we have discussed. So now it may be in order to discuss the systematic manner the various extraction systems used for the extraction of different metal ions, we will have to classify them into certain groups based on different approaches. So, several classification schemes are there. So, it may be important to point out here that the list of metal ions extractants is very large. They range from simple to complex molecule and single compound to mixture. So, with this background, a logical consequence scheme to be that whatever may be the criteria of classification, it may not yield a universal system. However, a simpler classification incorporating the mechanism of extraction and the extractant used into different types as distribution of simple molecules, extraction by compound formation, extraction by solvation, extraction by ion pair formation. So, we'll discuss one by one. Distribution of simple molecules. This involves the distribution of simple covalent compounds or covalent molecules like Cl4, mercury bromide, and arsenic bromide between aqueous phase and inert organic solvent. So simple molecules, that means they will not associate or dissociate. So depending upon the solubility, partition coefficient, you have to separate these things. So it is very simple. Then extraction by compound formation. When it will form compound, the reagents which fall under this category are liquid cation exchanges. Already we are giving some idea. These extractants operate at least formally by the exchange of H plus ion in acidic, that is organic compound, with the cation present in the aqueous phase. The ion is the acid, okay, organic compound, so there will be exchange, so it will be Ma X plus or Hn plus. The process is similar to solid liquid ion exchange with HA equivalent to one ion exchange resin, although there is some similarity between the reagents of this class and solid ion exchange, very important difference exists. So extraction by chelating agent, extraction by acidic organophosphorus esters, organophosphorus esters, and extraction by carboxylic and sulfonic acid. There are some. These are the examples. So when we move for the chelating agents, so we'll do some, we give some chelating ligand which will form chelate complex. So the chelating agent act as a weak acid and contains a donor group so as to form a bidentate chelate with the metal. So the hydrated metal chelates are poorly extractable in nonpolar solvent which do not have tendency to replace the water of hydration. So when you use the chelating agent for extraction. Second one, acidic organophosphorus compounds. Here alkyl phosphoric, phosphonic and phosphonic acids, phosphinic and phosphonic acids fall under this category. So when you are using phosphonic same, there will be exchange because phosphonic or phosphonic acid, they are tribasic acid, dibasic acid. So there will be exchange in multiple steps. So in this case, MCH-2. So one HMHX form metal and H plus will be released. So this will remain in the extraction. This will mean that the extraction is proportional to the mth power of dimer concentration and inversely proportional to the mth power of the proton concentration, where m is the charge on the metal ion. The type of alkyl and aryl group of the organophosphates will influence the acidic nature of the reagent. Increase in the chain length or branching of the substituent will decrease the acidic strength, although the main mode of action of this extraction is that cation or hydrogen exchange. There are numerous cases where the coordination of the phosphoryl oxygen occurs also. So these some examples are there, and with the acidic organophosphorus compounds can be used. Then the carboxylic and sulfonic acids. In this case, the metal extraction of these extraction is complicated by their state of aggregation in solution. You can see here. polymerization of these acids. The polymerization of these acids, although does not go beyond dimers, but the extensive aggregation of their salts play a significant role in their extraction. The bulk of available data on the extraction by carboxylic acid is on normal or branched chain monocarboxylic acid with 7 or more carbon atoms in the chain. Under certain specified conditions, the aliphatic and aromatic hydroxyl, carboxylic and dicarboxylic acids can also extract certain metal ions. Various benzoic acid derivatives, dinitrobenzoic, cinnamic, and phenyl acetic acid, and amino and perfluoro derivatives of N-carboxylic acids have also been as factor. Then move to the extraction by solvation. That means solvent molecules they will be aggregated in the complex, the interstitial voids. So by solvation, solvation increases the solubility of inorganic species in the organic phase. The oxygenated solvents like ethers, esters, alcohols, and ketones, and organophosphorus esters solvate the proton and neutral inorganic species, making the extraction of the acids and salts feasible. The simple examples are barium nitrate, ether, diether, then nitric acid, TBP, VO2 NO3, TBP2, and S plus TBP4, ReO4 minus, where this TBP is the N-butyl phosphate, tri-N-butyl phosphate. So the large variety of solvating molecules they can be grouped to two distinct categories as the reagents containing oxygen bonded to carbon, such as ether, ester, alcohol, and ketone, and the reagents containing oxygen or sulfur bonded to phosphor, example alkyl phosphates and dialkyl thiophosphates. So this first one extraction containing carbon oxygen bond. Okay, so in this case we can use alcohol, ether, where carbon oxygen bond will be there. So in this case, the function of the salting out takes place here. As regard as the extraction of metal nitrates, a particular aspect has received social attention, the role of salting out agents. So it has been observed that the addition of nitrate salt to aqueous phase greatly enhances the extraction. The extraction is of uranyl and thorium nitrate in either is greatly enhanced by addition of ammonium nitrate. It has found that other metal nitrates could be used for this purpose, but the multivalent nitrates which pronounced tendencies, hydration tendencies provide proved to be the most effective. The function of the salting out agent is considered to be threefold as is given below. So these are the some consequences. Then extraction containing phosphorus oxygen bonds. So general structure of esters and organophosphorus acids, trialkyl phosphate, trialkyl alkyl phosphate, dialkyl alkyl phosphate like dibutyl butyl phosphate, TBBP, alkyl dial phosphonate, butyl dibutyl phosphonate, trialkyl phosphine oxide, R3PO. So one phosphorus oxygen bond there which is substituted by three alkoxy groups, two alkoxy and one alkoxy and one two alkyl and three alkyl. So depending upon which one we can give the idea of the solvent extraction. Then extraction by lone pair formation. You have the amine. extraction of species formed due to interaction between the anionic metal species in aqueous phase and cation furnished by organic phase. The strongly basic high molecular weight amines are able to extract the metals by forming the ion pairs with anionic metal complex. The other extractable pairs found by quaternary phosphonium, arsonium, phenyl, phenylaluminum bases are also included under this category. Some of the examples of different types are given here. Under this class of extraction, high molecular weight amines are received maximum attention. So amines can be used as this ion pair formation. Then the extraction by crown ethers is a new class of reagents. Like crown compounds are first and emerging as potential extractants. Initially, the importance of these compounds was highlighted because the fact that they are good extractants for alkaline and alkaline earth metals. Alkali metals and alkaline earth metals. And thus, the separation of these metals by solvent extraction becomes possible. So these are multi-dented macrocyclic ligands with oxygen, nitrogen, or sulfur as the donor atom, is crown ethers. So the binding of the metal is determined by compatibility of the cavity size of the crown compound and the radius of the metal ion. So the first few compounds of this series were crown ethers, which consist of cyclic ether groups CH2O, CH2O groups to form cyclic compounds containing 12 to 24 ring oxygen atoms. So these crown ethers, they contain a central varying size of hydrophilic cavities depending upon the size of anatomic oxygen. So if size of ring increases, then the cavity which is ringed in electronegative binder polyether oxygen atom. The oxygen atoms are surrounded by a polar of CH2 group, methylene group, imparting the hydrophilicity. So oxygen gives hydrophilicity, CH2 or methylene gives hydrophilicity. A complex with the cation converting into lipophilic species which extract the organic solvent. The complexes are composed of two ionic species held together by electrostatic attraction. So these are some examples, different types of solvents or the components which are used for extraction. Then we move to next to the diluents and modifiers. So what are the diluents? Why we use a diluent? We have to dilute. One particular point which should be kept in mind is that the majority of the extractants are either solids or their viscosities are too much high for their use for their direct use in the solvent extraction. So therefore, in common practice, we use or we dissolve them in a suitable solvent, which is known as the diluent. Thus, the diluent refers to the organic liquid in which the extractant is dissolved to form the solvent. In majority of the cases, the diluent comprises the major portion of the solvent. During solvent extraction, sometimes the formation of a third phase takes place, and to avoid this, a modifier may also be added. So, in view of the importance of the diluent and modifier to make their extractant system workable. So, diluent, the reason of using a diluent now clear. So, they are mainly why we are using. They are mainly used to decrease the viscosity of the extractant. Generally, the extractant used for commercial solvent extraction process are viscous liquids, and they cannot be used as such. Depending upon the metal to be loaded, an appropriate concentration of the extractant is to be used. Thus, diluent provides a solvent for preparing the solution in the extraction of desired, desired concentration. Another role of diluent is to decrease the emulsion formation tendency. A number of extractants are surface active agents and therefore at high concentration tend to emulsify, especially at the high agitations. The diluent improves the dispersion and coalescence properties of the solvent. These are two very important aspects for a solvent extraction process. So therefore, different their essential characteristics of the diluent should be mutually soluble with an extractant or modifier. It should have high solvency for the extracted metal species. It should have low volatility and a high flash point. It should be in its own right insoluble in aqueous phase. It should have low surface tension. It should be cheap and readily available. So these are the properties by which you can select the diluent. Similarly, the modifier. So the formation of third phase is temperature dependent. Usually, increase in temperature will result the disappearance of the third phase. So then you have to use the modifier. Modifiers are involved solvating agents like isodecanol, 2-ethyl hexanol, para, nonyl phenol, and TVP. So these things are the modifier which are used. So okay, that ends the chapter 1 and 2. What we will discuss next chapter. So you have some further questions. There. Yeah. Okay, thank you. Any doubt?
Sir, today audio was not so good, sir. For
Okay,
tomorrow, please, sir.
okay. I will check that one. I have to take the class. That's why I find the time
Yes, sir.
for it. Yeah, thank you.
Thank you, sir.